Okay, so the webinar is now being recorded. We will be able to see it later. So thanks everyone for joining. My name is Patrick Goldschlegel. I'm an engineering manager in Elimination, now part of ARM. And today we're going to discuss a few things about workload balancing and how to resolve this kind of problems. So the agenda for this session is to go through a few things. So first of all, the importance of load balancing in HPC. We will see what are the different challenges associated with this task, but also how to identify load imbalancing problems and how to get rid of these issues to improve the applications and how they run at scale. Right, so before starting, a very small introduction about Alinea. Most of you are probably familiar with the company. Some of you may not be. So Alinea is a company that has developed for many years now software development tools for the HPC market. And as of December 2016, we have been acquired by ARM. So our objective remains unchanged. We want to remain trusted leader in cross-platform HPC tools. This is very important, even though we are part of ARM, which is a designer of chips who create chipsets. We want our tools to remain available cross-platform. So we will keep supporting all our customers who are using x86, Knights Landing, IBM Power Systems, or NVIDIA GPUs. This acquisition is a very good thing because as part of ARM, we now have a much stronger financial company who's backing Alinea, which means that we are able to hire faster. We are able to deliver our roadmap faster, which means that our products, our tools, will continue to evolve very positively in the future. And again, we are very committed to working with top vendors such as Intel, IBM, but also tier one vendors such as Cray, IBM, Atos, or HP, or all the major vendors providing HPC systems. And we will keep developing unique features as part of our products to ensure that you as a user are successful using these HPC systems. So in Alinea, we are designing multiple tools, including debuggers, profilers, and application analysis. And as part of the promotion, we have started a campaign which we call the Alinea Performance Roadmap. And as part of this campaign, we are covering a wide range of topics. Sorry, was there a question? No, this wasn't the question. Okay, so as part of this campaign, we're covering a very wide range of different topics, including I/O. So there was a webinar a few weeks ago about I/O optimization. We talked also about vectorization, and today we are focusing on balancing the workloads of applications and of different jobs. So in order to achieve this, we will rely on Alinea Forge, and more particularly on Alinea Map, which is a parallel profiling tool for HPC applications. So let's deep dive into the topic. So why is load balancing important? So from an end user perspective, you're using your application, and most of the time everything will be fine. But sometimes there may be issues where the workload itself is not well balanced inside your application. So this means that the domain decomposition is not done in the best possible way, and this usually translates into problems that are not necessarily obvious. So for instance, an application could potentially take a longer time to complete, which means longer time to resolution of the application. You could be wasting CPU hours, but for an end user, this directly means that the budget and the allocations you've been given on the CPU on the machine is actually being wasted because processes are being idle or not doing any useful work when they could be. This issue from the end users translates into more pressure on the systems If a lot of users have load balancing problems, it means that the supercomputer is potentially loaded with workloads that are not running very, very well. So even though the machine and the system usage can be very high, it potentially means that 20, 30, 50% of the machine time is actually being wasted. So from a system administrator point of view, either the problem is resolved and the applications are optimized, or the system administrators will need to request for more hardware in order to absorb the demand of the end users, which in turn creates a problem for system owners who have to invest into more hardware, who have to pay for a bigger energy bill, and which also means that the clusters they've purchased gives them a smaller return on investment. So in order to resolve all of these problems, we need to focus on the applications, how they run, and what actually happens. So when you're using a parallel application, there are multiple types of load balancing issues that you can see. But one of the key things is that there is a very strong asymmetry between some processes that have too much work and some processes that do not have enough work. And we're going to illustrate this with a small graph. So if we take this first example, so basically we are in the scenario where we are running on 4 processes, so 4 cores of a machine, and one of these processes does not have enough work. So let's assume that the total runtime of the application is 100 seconds, and the process 0 only has 50 seconds worth of workload, whilst all the others have 100 seconds worth of workload. This means that the time to completion of this application is 100 seconds, but we are effectively only using 350 seconds of the CPU time which is available. So if we make a small calculation, so 350 seconds actually used divided by 400 seconds, which is the total CPU time available, we are using 87.5% of the machine, which is good, but not perfect. So if we did optimize this, we could potentially reduce our time to resolve to 87.5 seconds instead of 100 seconds. So if we take the same example with 4 processes, but process 0 has too much work. In this case, you can see here on the small picture that actually the behavior of the application is much, much worse, because our processes 1, 2, 3 are only spending 50 seconds of time doing actual useful things. So if we do the same math, the same calculation, we can visualize very clearly that in this particular case, the overall efficiency of the application and the actual usage of the machine is fairly bad, because we are only using 250 seconds of CPU time when we have been allocated 400 seconds, which means that the efficiency is down to 62%. So this shows that one of the key issues we need to be able to detect and resolve is identifying processes or groups of processes that have more work than the others and that have too much work compared to the others. So how do we resolve this kind of issues? Typically, these kind of problems are visible looking at synchronizations. So typically, if we look at MPI collective calls, such as MPI barrier or MPI broadcast, what would happen is that the group of processes that finish early during the execution will start synchronizing early into these barriers, into these collective calls. But the one process that is too late, because he has too much work, will only arrive much, much later. So this is illustrated in this picture, and you can see here that whilst all the processes are inactive, basically there will be no communication happening in there. So if this is an MPI collective call, typically it would be associated with no actual data transfer. So the MPI bandwidth associated with these calls would be 0. So this is one of the things we can be looking for in a profiler to identify this kind of problems. If we are using a multi-threaded environment, and instead of using MPI calls, we're using threads and mutexes and locks, it would be exactly the same. The name of the functions we would be looking for would be slightly different, but essentially it's the same thing. What we would need to optimize, if we want to improve this, is really the process or the thread or the group of processes that are taking too much time. And we want to redistribute their workload evenly to all the other processes to ensure everything works fine. So this is a typical problem that can be easily spotted with Alinea map, and we will see this in a demo in a few minutes. The second typical issue about load balancing is what we call cascading dependencies. So in this scenario, basically we have processes or a group of processes that do not start at the same time. And this is usually due because of something that happens in the application which is sequential, and that translates into an imbalance later during the execution. So to identify these problems, what we need to look at is basically a triangle pattern in the profile, because the processes are start entering functions one after the other, which is why we call it cascading dependency, and it obviously creates problems. And you can see this kind of triangle shapes by looking at the picture. So to resolve these problems, first of all, we need to find where this is happening, but we need to look in the history about where this is happening, when this is actually starting during the execution. And once we have found where this is actually starting, we can address the flow, we can address the workload and make sure that all the processes start at the same time and not one after the other. And this will ensure that we minimize and we reduce the runtime of the applications. So how do we actually balance the workload? So this is a very complex question, and actually there's no easy solution. There are multiple types of load balancing techniques. The first one is what we call static load balancing, where we actually assign a defined sized workload to each of the processes, and we try to make sure that they all start and finish at the right time, so we do not have any synchronization. So the most obvious one is what we call owner's compute, where we actually distribute a data set equally across multiple processes. This is fine when we are doing easy matrix multiplications or other linear algebra equations. But this actually becomes a problem if we are talking about much more complex domains with much more complex domain decompositions. The other obvious way of doing static load balancing is by having multiple independent tasks, and if we can predict, or if we know how much time will be spent by all these different tasks, we can manually interleave them and ensure that the workload starts and finishes in a nice and decent fashion. But unfortunately, this is not always easy. Usually what we find is that in real-life applications, it is really something that is completely dynamic, which means that the load associated with processes changes over time depending on what is happening. So there are a lot of workload models that exist. You can have a process or a few processes that are in charge of scheduling and changing the workload associated with all the processes. So there are a lot of different techniques that are available. So again, we will not have time to look at all these different things. I'm just sharing with you a few pointers and a few keywords, and if you want to, you can have a deeper look into these different topics. The one topic that I would strongly suggest that you have a look at is what we call space filling curves. So this is basically a mathematical theory which is extremely powerful when it is applied to algorithm, because it does not only ensure that all the processes have an equal workload to work on, but it also helps ensure that all the processes have their data close to them, which means that we're taking care of data locality and ensure that whatever a process is doing doesn't need to be looking at data which is stored far away in memory on a different node or something like this. If you want to push the idea even further, there are very modern algorithms that have been developed around swarm intelligence. It is also a very fascinating topic, which basically relies on what can be observed in nature, for instance, with ants and basically animals who would be working together, sharing a workload to achieve a common goal. So again, these ideas can be translated into algorithms and into HPC models to be used within applications. So, is there any question at this stage? I would encourage you to ask your questions in the chat. I will answer all of them either now or later during the execution. So don't hesitate to start typing. I'll be more than happy to answer any questions you may have. So whilst the questions are flowing in, I will now start the demonstration. So I'm going to show you a few things, and hopefully this will be interesting. So in this small folder here, I'm running on the Linux machine, and I have 3 versions of the code, which is basically a matrix multiplication. So what I'm going to do is I'm going to start by showing you the code, showing you how it works. It's very, very simple. So this is an MPI code written in C, and basically when we're looking at this application, it does the following things. So to begin with, we initialize a grid of processes using MPI that we are going to distribute across 2 different nodes. So we are going to use 16 processes and 2 nodes for this example. So at the very beginning of the execution, our process 0 will initialize 3 matrices, A, B, and C. And we will basically send these matrices across. So these matrices will be split into equal chunks of equal sizes and will be sent across to all the different processes that will be doing this calculation. Once all the processes have received their data, we will start doing a matrix multiplication operation. So each process will take his slices, will do C equal A multiplied by B, and will send the results back to the process 0, which at the end will write the data on the disks. Once the data has been written, all the processes are destroyed and the application finishes. And we have our matrix multiplication. So what we need to do is, first of all, if we want to run this application, we need to compile it. So to do this, I'm just using make. And as you can see, I have compiled my code with optimization options. So I'm using O3. The only requirement, if we want to profile this code and see how it actually runs, is to use the -G symbol here. So this ensures that we create the debugging information as part of our binary in order to be usable with Alinea map. So I would typically start this application, for instance, using this command. So typically, I'm using MPI run on 4 processes with nmod5_c.exe. So this is the command I would be submitting to my job scheduler. And what I'm going to do is, instead of running like this, I'm going to use map-profile in front of this MPI run command. And this will actually create a .map file, which is the profile of my application, which can be visualized with Alinea map, so the profiler. So to open the file that has been created, so typically I'm looking at this particular file here. This is one output that I have generated. I'm going to open this file with my profiler inside the graphical interface, and I'm going to see what happened during the execution. So in Alinea map, you can see here we have multiple things. So we have on the first, at the top of the GUI, we have what we call the timeline. So this shows what happened throughout the execution across multiple metrics. So at the top of the graphs, we have the main thread activity, which is basically very generally what happened during the execution. So if we have something that is blue, this means that we are doing MPI communication. If we have green stuff, we are looking at CPU calculation, so something happening on the CPU. And the cool thing is that when we're looking at all these different colors, Alinea map will tell you what lines of codes are responsible for these colors. So for instance, if I would like to see what is happening here, I select this time slice, and map is saying that I have spent most of my time during this mmod calculation, but there are also been some time spent in send, in receive, etc. So based on this information, we want to look for workload imbalances. And what we've seen earlier in the slide was, the first example was about a process that had too much work. And basically it translated into one process doing something and all the other processes doing something completely different, which is the synchronization. And what we noticed is that this particular pattern is clearly visible here. So if we look at this particular section of the code, we can see that for most of the application, most of the processes are doing something blue, which means that they are doing MPI communication. If we want to double check the quality of this MPI communication, we can have a look at the MPI metrics. So if we go to the metrics menu, you can see here different entries with MPI metrics, and the ones that we are interested in is MPI point-to-point bytes and also MPI collective bytes. So this will tell us what is the bandwidth associated with the MPI calls during this particular section. And if we look at both these metrics, which cover every MPI communication in the MPI standard, we can see that all these have, for this particular time slice, a bandwidth of 0. So this means that we are not using MPI to synchronize, to share data or to communicate data between processes. We are using MPI to synchronize our processes, and they are waiting. They are not doing anything useful. And this is correlated with what we can see at the bottom here, where most of our time is spent in this MPI finalize function, which effectively does nothing. It's just sitting, waiting for all the processes to reach this particular line. So we are typically here in a scenario where one process has too much work, whilst all the others are waiting in a synchronization. So what is happening? If we look at the second line here, the tiny little 6.2%, we see here that our process 0, so if my rank is 0, it means that the process 0 is executing this particular loop. We see that this process is spending time writing data in a file. So this is our bottleneck. We have here a section of our code which is completely sequential, which is only done by our process 0, which is stopping our program from finishing. So if we want to resolve this load balancing issue, we need to fix that. We need to change this portion of the code and do something about it to make it better. We can even estimate how much time it would save by doing this. So if we select this time slice here, we see that this particular section of the code represents 34, almost 35% of the total runtime. So if we manage to improve this, we are going to save 30% of our run. So this is what we're going to do. We're going to replace this particular section, and instead of having a sequential mWrite, we are going to use to make a small modification on the code, and we are going to use this instead. So we will, so if I go back at the end of my execution, here, instead of asking for process 0 to write the data, I'm going to use an MPI IO set of function, which is basically asking my program to run the data in parallel. So all the processes will open the output file and will write their own result inside that file before closing and before finishing the execution. So by doing this, we are effectively parallelizing the last section of our code, and we are redistributing the workload, trying to ensure that instead of having one process who has to do everything, all the processes have an equal amount of work to complete by writing this data. So we're adopting a known-as compute and static load balancing technique based upon what we've seen earlier. So if I compile this code and run it again with a linear map, so we're using the same methodology, just use map --profile with the name of the executable. So map profile MPI run -n4 mode6 underscore c.exe. So we execute this particular command, and we get as an output this particular file that we can open with Alinea map. And this is the result. So first of all, we notice that the actual runtime of the application has been massively increased. And as we expected, we have moved from 140 seconds down to 95 seconds, which means that the gain we expected of 30% runtime is actually verified. We have saved a massive amount of time during this execution. You see that the overall profile has changed a bit. Instead of having a massive chunk of blue at the end, now we have a massive chunk of orange, which is basically in a linear map, means that we are doing file IOs in our code. And if we look at the end section of our code, here we look at what's going on. Alinea map basically reports that we are actually writing data, doing a small barrier, and that it is finished. And instead of spending 30, 40 seconds doing this, now our actual write of writing the data is down to 9 seconds, which is the number we can see here in the GUI. So this is a massive improvement, but the code is still not optimized yet, because we still have a lot of time spent in MPI calls at the beginning, and we have this massive orange thing here at the end of the run. So if we want to see what's going on again, we use map, select a time slice, and what we see is that almost a lot of the time is spent in this MPI file open. So again, what is happening? What are we actually doing? We can look at the different presets, the different metrics that are available. And what we can see here is that for this particular section of the code, even though we are doing an IO and then we are opening a file, there's absolutely no bandwidth associated with this read and data or the write data transfer. So we are in the exact same scenario than before, where we are stuck in a synchronization, but we are not actually writing or communicating anything useful in the program. But what really catches our attention is the shape of the profile. Because if you look at this shape here, you can see a triangle pattern, which is what I introduced. And I suspect that the triangle we see in orange for the IOs is actually a consequence of what is happening earlier in our execution, which is here visible in blue. So what is happening earlier in the code? So we select the time slice, and Alinea map is telling us that we are spending time receiving data. So again, this is interesting because MPI receive is a point-to-point MPI communication. It is synchronous, which means that processes will not exit this line of code until they've actually received their data. And this is a problem because we're spending way too much time on this. So while we are stuck, again, synchronizing what is happening, well, the cause of this synchronization is, again, this MPI send here, which is, if we scroll up a bit and if we look at how the code is written, is actually inside this if conditional loop, which is only delivered by rank 0. So only rank 0 is executing this, and is actually doing a series of MPI send, which are sequential blocking calls, and because they are happening in serial mode, our processes are waiting. So what is happening here is that at the beginning of the execution, here, our process 0 sends slices, apologies, our process 0 sends slices to process 1. Once the process 1 receives data, able to start the calculation straight away, which is why we have green activity. And as soon as the process finishes, it starts waiting in the MPI file open. And what we see here is that these transfers that happen at the beginning are actually going very, very fast because we have a very steep column here. We can also look at the MPI metrics. And we see that the bandwidth associated with the MPI calls is actually fairly high at this stage. But this bandwidth reduces dramatically when we're looking at this later stage. This is caused by the actual topology of our cluster, because we are using a cluster which does not rely on InfiniBand, but relies on Ethernet communications. So when we are sending data across to processes that are close inside the given node, the bandwidth is very high. But once we switch to inter-node communications, so from one node to the other, the bandwidth drops. And this is why we have this very long calls here that are taking place and that are penalizing the whole run. So how do we resolve this? So again, basically the problem we have is that this particular section of the code with sending the data is very sequential. So we need to parallelize it and ensure that instead of having one process doing all the work, which causes a cascading dependency, we need to make sure that we can address this in parallel. And we can achieve this by using a different type of call. So if we look at our example 7 here, we are going to use, instead of doing MPI sends, we are going to use MPI broadcast and MPI scatters, which means that we are using a collective operation in order to send the data. So with this last bit of optimization, if we look at the result and what actually happens, what we see here is now we have a perfectly good profile. So don't pay too much attention about the runtime, because the actual size of the data set and the size of the matrix multiplication is different than previously. But what you can see is that the communication is going much faster. So we're wasting much less time on the MPI communication sending the data, but also at the end, because we have addressed the cascading dependency at its source, we have now also optimized the time we spend writing the data and finalizing our application, which means that we have seriously optimized our code, which is now running most of its time on CPU calculation, which is what we want, because this means an efficient supercomputer, and this means very good throughput on the machine. So by going through this very small example, we've covered multiple things. First of all, we've seen what happens when one process has too much work. And this can have a dramatic impact on the runtime of your application, on its efficiency, and ultimately, if you're a user, it is very bad because you're burning your CPU allocations. The CPU time that has been given for your scientific project is being wasted because of poor optimization. So the good news is that in most of the cases, fixing these kind of problems using the right profiling tool can be very easy. It's not always. There can be a lot of very advanced techniques to fix it. But as you have seen here, fixing these problems on this particular example were fairly easy. So once we've fixed and we've ensured that all the processes have the same amount of work, we have also worked on cascading dependencies, ensuring that processes are starting and stopping the calculation at the same time, and that we do not have processes starting one after the other. And by making these two changes, we've been able to dramatically improve the overall runtime of the application. So initially, we were looking at an application running on for 140 seconds. Our first modification gave us a 30% speed up. And now again, by modifying this, we also have a very nice speed up that ensures that we get our results much faster. Right, so I've been talking a lot. Do you have any question about the demonstrations or about the tools? Is there anything you would like me to describe in more details? No questions? So I invite you to drop a message in the chat if you want to. So from here, basically, well, I hope that this session was useful and that you've been able to learn one or two things. So first of all, I encourage you to get a free license, so you can get this fairly easily on our website. If you think that you may have load balancing problems, I encourage you to profile your codes and ask us for help if you need. And if you find something, if you manage to increase the performance of your application, really do not hesitate to let us know about it. We love this kind of stories, and we would be happy to tell the world about it, doing case studies and these kind of things with you. This is something we're very keen on doing. So it looks like there is one question. So one question is, where can I get the free license? Right, so when I say free license, I'm actually talking about trial licenses. They are available on our website. So if you go to www.alinea.com/trials, you can fill in the form, give us your details, your email address. So the email address is important because this is where the license will be sent out to. And with this license, you get access to all our tools. It's valid for 1 week. And it gives you the ability to profile, debug applications on 64 processes on all architectures. So we support ARM, x86, Knights Landing, power systems, GPUs, all of this is supported. So you get full access to the tools. If you want an extension, either in terms of duration or in size, we're happy to extend the trial license for 1 month. And again, if you want more processes, if you want to run on bigger codes, feel free to do so. You're more than welcome. Okay. Dan, you have a question. So thank you very much, everyone. Again, I'm staying for a few more minutes, so feel free to ask your questions. And otherwise, have a very good week and talk to you very soon.